In early 2025, a transcontinental telescope array detected a deep space signal so violently powerful, astronomers immediately gave it a nickname. They called it RB Float, the radio brightest flash of all time, striking our detectors from a galaxy 130 million light-years away. For a fraction of a blink, that single invisible wave released as much energy as our sun produces in several days. And just like that, it vanished. This is the raw millisecond problem of fast radio bursts, and it is fracturing modern astrophysics. We confidently thought we solved this mystery back in 2020, when we caught a highly magnetic dead star firing a similar flash. But now, next-generation observatories are finding these exact same bursts buried inside ancient dead galaxies, where those stars absolutely cannot exist. To understand why this phenomenon refuses to become one simple story, we have to look at the physical impossibility of the signal itself. Before we debate what builds these cosmic engines, we must confront the extreme scale of the energy they leave behind. A fast radio burst is an intense pulse of electromagnetic energy lasting just 1/1000th of a second. If you look at a radio waterfall plot, you don't see a gradual curve. You see a brutal, instantaneous vertical spike cutting straight through the background static. Because they are so incredibly fast, catching one used to require an extreme stroke of luck. The very first discoveries at the park's observatory were only found by digging through years of archival data, long after the cosmic flash had already washed over Earth. That observational bottleneck shattered when Canada built the CHIME telescope. Instead of pointing at a single target, CHIME constantly stares at a massive strip of the sky, acting like a digital net. By 2025, it pushed the catalog to over 4,000 confirmed bursts. With thousands of clear detections, the physical constraints become undeniable. To compress days of solar output into a millisecond-long radio wave, the emission region has to be extremely compact. You cannot generate that kind of concentrated, sharp spike from a sprawling, diffuse nebula. Basic physics dictates that the engine driving these bursts can be no larger than a few hundred kilometers across. We are looking at objects the size of a small country generating enough electromagnetic force to be clearly heard across billions of light years. Early in the investigation, researchers genuinely wondered if these signals were just local interference. In fact, a famous set of fake signals called peritons were eventually traced to a microwave oven being opened prematurely at an Australian observatory. But true fast radio bursts have a specific signature that cannot be faked by terrestrial interference. As we will see, their light is smeared out in a highly precise way, proving definitively that they have traversed vast oceans of intergalactic plasma. Even with 4,000 confirmed events, we're likely only seeing the absolute brightest flares. Current telescope sensitivity limits mean a massive population of fainter bursts is constantly hitting our planet, entirely undetected by the hardware we have today. Our most reliable working model points to magnetars, ultra-dense neutron stars with magnetic fields trillions of times stronger than Earth's. A violent crustal failure on one of these stars could theoretically channel enough energy to fire a radio beam this intense. We know these flashes are immensely powerful, and the sheer scale of the energy is not up for debate. But a flash alone doesn't tell us how we prove these signals are crossing the universe, rather than just firing off in our own stellar neighborhood. To figure out if a radio flash is actually crossing the universe instead of just firing off in our own stellar neighborhood, astronomers don't just measure the brightness. They have to read the signal's travel history, looking at the exact shape of the radio wave when it hits the dish. This is where we encounter a phenomenon called dispersion measure. When a fast radio burst leaves its host galaxy, all of its frequencies, from the high-energy peaks to the lower bands, burst outward at the exact same instant, perfectly aligned. But space isn't completely empty. Between the galaxies lies a thin soup of ionized gas and free electrons. As the radio pulse travels through billions of light years of this plasma, it experiences a tiny, invisible drag. And not all frequencies handle that drag the same way. The high-frequency radio waves punch through this intergalactic plasma slightly faster. By the time the signal reaches Earth, the lower frequencies have fallen behind. Instead of arriving in a single, sharp spike, the flash is smeared out over a fraction of a second. If you look at the data coming from observatories like the CHIME telescope in Canada, this delay is impossible to miss.
In their waterfall plots, the signal creates a sweeping diagonal line, a downward drifting frequency that astronomers sometimes call the sad trombone effect.
A dense nebula wrapped tightly around the engine could mimic the dispersion of deep intergalactic space. Recent models have to carefully separate the plasma of the host galaxy from the vast stretches of empty space in between. If we miscalculate how much material is immediately surrounding the source, we could get the distance and the true energy of the burst wrong. The only way to completely disprove this extragalactic model would be finding a heavily dispersed burst that optically tracks back to an object inside our own solar system. So far, every high dispersion signal we've ever caught points resolutely into the deep cosmos. The dispersion measure confirms we aren't just seeing local glitches or terrestrial interference. We are watching massive, rapid-fire detonations happening billions of light years away, releasing days' worth of solar energy in a fraction of a blink. This realization launched a global hunt for the source. With the staggering distance confirmed, astronomers began searching for the extreme astrophysical objects capable of firing these signals across the void. The theoretical math pointed directly toward one specific type of dead star, and for a while, the community thought they had their answer. In 2020, we finally caught one of these engines red-handed, firing off a burst right here in our own galaxy. It felt like a total victory. So why didn't that discovery actually solve the problem? For a brief moment in 2020, the mystery seemed completely solved when an alert triggered not in a distant corner of the universe, but right here in our own cosmic backyard. We finally had a target we could clearly see. Astronomers caught a brilliant millisecond flash of radio waves originating from a known dead star called SGR 1935 plus 2154. This object is a magnetar, a hyperdense neutron star packing a magnetic field around 1,000 trillion times stronger than Earth's. When the crystalline crust of a magnetar fractures under extreme magnetic stress, it triggers a catastrophic starquake. This violent reconnection of magnetic field lines was theorized to blast out a highly concentrated, lighthouse-like beam of radio energy. In April 2020, global observatories finally saw this theoretical mechanism play out in real time. Telescopes recorded a millisecond radio burst perfectly synchronized with an intense flare of X-rays coming from that exact galactic magnetar. This simultaneous dual-band detection was the smoking gun the astrophysics community had been searching for. It proved definitively that highly magnetized neutron stars possessed both the raw energy budget and the mechanics to power fast radio bursts. The discovery brought a massive collective sense of closure to the field. The standard model appeared to be perfectly locked in. Young, highly active magnetars were the definitive single-origin engines firing off these mysterious flashes across the cosmos. Even today, deep monitoring of this specific Milky Way magnetar continues. Recent 2026 astronomical studies are actively analyzing its internal rotational glitches, trying to map exactly how structural fractures inside the neutron star reliably trigger these massive radio eruptions. The magnetar model was elegant, incredibly powerful, and most importantly, backed by verifiable local data. The only problem with this textbook resolution is that it created a deeply false sense of security among researchers. When scientists actually sat down and compared the raw output numbers, a massive energy gap became impossible to ignore. Our local galactic burst was actually orders of magnitude weaker than the deeply extragalactic fast radio bursts crossing billions of light years. This glaring discrepancy raised an incredibly uncomfortable alternative interpretation. What if this local galactic event was actually a completely different physical class of eruption that merely mimicked the specific radio profile of true cosmological fast radio bursts? Believing the 2020 discovery solved the entire puzzle became a dangerous trap. It successfully proved that a young magnetar can produce a fast radio burst, but it absolutely failed to prove that they create all of them. To be clear, the baseline physics still hold up for certain events. Highly magnetized neutron stars undeniably possess the extreme environments required to power at least the lower luminosity radio bursts we detect in the local universe. But as next-generation telescope networks rapidly expanded our catalog from a few dozen isolated bursts into thousands of recorded flashes, this pristine single-engine theory began to totally fracture under the sheer weight of contradictory observational evidence. The narrative was about to break completely.
Because if magnetars are the only proven engines of fast radio bursts, why are telescopes suddenly tracking these flashes to ancient, dead galaxies where young magnetars cannot possibly exist?
As telescopes cataloged thousands more bursts, their locations started breaking the fundamental rules of stellar evolution. We thought the 2020 galactic discovery was the final word, but the universe had a completely different script ready. The standard model relies entirely on young, highly active magnetars. These intensely magnetic neutron stars are the ultra-dense remnants left behind after a massive, short-lived star detonates in a supernova. Because massive stars burn out fast, magnetars must be born in active stellar nurseries. To find a standard magnetar, you look inside a vibrant, gas-rich spiral galaxy, a chaotic environment where raw hydrogen is constantly collapsing into new stars. For years, this matched the data perfectly, as most fast radio bursts were traced to these active star-forming neighborhoods. But in early 2025, astronomers traced a powerful repeating signal known as FRB 2024-0209A. Instead of pointing to a bright spiral, the precise coordinates landed on a massive red elliptical galaxy. This host structure is about 11.3 billion years old, and it is entirely quiescent. In astrophysics, an old elliptical galaxy is effectively considered a dead zone. It exhausted its raw star-forming gas supplies billions of years ago. There are no massive blue stars left to explode, which means the expected population of young magnetars here is mathematically zero. Making this situation even more impossible, the radio burst didn't come from the dense core. Astrometric localization placed it roughly 130,000 light-years away from the center, firing from deep within the sparse, lonely outskirts of the galactic halo. Faced with a paradox, the initial assumption was an optical illusion. Astronomers questioned whether this was just a chance alignment, proposing that the true source was a much younger, hidden galaxy positioned perfectly behind the dead one. But deep optical imaging and rigorous statistical probabilities heavily ruled out a background mirage. The localization is absolute. The burst is undeniably anchored to this ancient galaxy, completely upending the young magnetar hypothesis that we just established. To solve this crisis, researchers looked at what actually survives in a galactic halo for 11 billion years. The leading candidate is a globular cluster, an incredibly dense, ancient swarm of stars held together by gravity, slowly orbiting the outer edges. If the engine is hidden inside a globular cluster, it requires a completely different mechanism of creation. Instead of a single massive star collapsing rapidly, you need a delayed formation channel. This happens when two ancient white dwarfs slowly spiral toward each other over billions of years. When those two dead stellar cores finally merge, they cross a critical mass threshold. The combined object violently collapses inward, triggering an event that can birth a new magnetar long after all standard star-forming activity in the galaxy has permanently stopped. To definitively prove this delayed merger theory, astronomers are proposing to use the James Webb Space Telescope. By focusing its advanced infrared sensors on the burst's precise coordinates, JWST could visually confirm the faint glow of that exact globular cluster. This discovery proves that fast radio bursts simply cannot be explained by one simple story. The extreme environments surrounding these sources demand that the universe has multiple, entirely distinct evolutionary pathways capable of generating these identical millisecond flashes. With the accepted timeline of stellar evolution broken, astronomers had to stop looking just at the host galaxies and start looking back at the signals. If a young dead star isn't the only engine, what are the repeating flashes trying to tell us about colliding binary systems? To answer that, astrophysicists had to look closely at the architecture of the bursts that happen more than once. The key to breaking the deadlock wasn't just finding more flashes, but tracking exactly how the radio waves twisted as they traveled through local space. By late 2025 and into early 2026, the 500-meter aperture spherical telescope in China, known as FAST, provided a massive breakthrough. Scientists were monitoring a specific repeating source called FRB 2022-1022A, which had been relatively quiet and unremarkable for over a year. Then, the telescope captured something entirely new. A sudden, violent distortion in the signal. The magnetic signature of the burst, called the Faraday rotation measure, surged to nearly 100 times its normal level before dropping back to baseline just 2 weeks later. This magnetic signature acts like a fingerprint of the immediate environment surrounding the burst. When radio waves pass through a dense, highly magnetized cloud of plasma, they twist. A sudden spike in this twisting meant a massive wall of plasma had temporarily blocked our view. Researchers realized this wasn't a solitary star acting alone. The plasma wall was a coronal mass ejection, a massive stellar eruption blowing across the line of sight. This proved the FRB engine was locked in a tight orbit with a larger, highly active companion star. But even within this chaotic binary system, the actual flash originates from a deeply constrained space. Advanced polarization studies confirmed that the radio emission is generated incredibly close to the neutron star, specifically within 10,000 kilometers of its surface, deep inside its magnetosphere. Confirming these orbital interactions is incredibly difficult because repeating bursts don't follow a neat, predictable schedule. You can stare at a known source for months and see absolutely nothing, which is why the continuous deep space monitoring capability of the FAST array was absolutely essential. There is still a boundary of uncertainty. Some astrophysicists argue that instead of a companion star, the observed modulation could be the slow precession, a literal wobbling of a solitary, highly magnetized neutron star, causing its beam to drift in and out of our line of sight. But the sheer density of the plasma measured in the 2026 data makes the solitary wobbling star model incredibly strained. To completely disprove the binary model, we would need to find a highly active repeater that shows absolutely zero long-term periodicity or plasma variation. This discovery forces a hard realization. Repeating bursts and one-off flashes might not look identical up close. Repeaters often show a complex downward drift in frequency, a characteristic sad trombone effect, which is rarely seen in the solitary flashes that light up the sky just once. Statistical clustering of these signals now points toward a profound progenitor diversity. We are looking at distinct environments, some bursts erupting from isolated, dying stars in ancient galaxies, and others firing from volatile binary systems constantly bathed in stellar winds. Regardless of whether a massive companion star is present or absent, one fact remains completely intact. The emission definitively occurs deep within a profound magnetic field, requiring physics so extreme that we cannot replicate the conditions anywhere on Earth. The evidence now points to a deeply fractured reality.
Magnetars might explain the flashes we see in our own cosmic neighborhood, while ancient, interacting binary systems must be responsible for the complex repeating patterns we see in distant galaxies. The simple story of a single cosmic engine is officially dead. So how are astrophysicists trying to stitch these contradictory environments into a working theory that explains both the solitary explosions and the repeating binary flashes? Because one environment cannot possibly produce all the bursts we see, theorists have drawn up two distinctly different blueprints. They are trying to explain how a highly magnetized engine could exist in a stellar graveyard billions of years old. The leading solution for these ancient galaxies is called delayed magnetar formation. Instead of a massive star collapsing quickly into a neutron star, this model relies on the slow, creeping interaction of dead stars over a massive timescale. Picture two massive white dwarfs locked in a binary orbit. Slowly, they siphon material or spiral closer until they merge. This triggers an accretion-induced collapse, violently forging a brand new, highly magnetic neutron star long after the surrounding galaxy has stopped forming stars. We can theoretically test this delayed model by looking at the dispersion measure of the radio waves over time. Pulses passing through the expanding shell of a white dwarf merger should show a measurable increase in dispersion, rather than the fading debris of a typical supernova. But delayed formation only solves part of the puzzle.
The deeper divide in astrophysics right now is the split between fast radio bursts that flash once and vanish, and those that repeat. Many scientists now believe we are looking at two entirely separate populations. The solitary flashes might be true cataclysms. Gravitational wave theory suggests that when two neutron stars collide and merge, they could release a blinding, one-off radio burst right before collapsing into a black hole. In this scenario, the engine destroys itself to create the flash. Repeaters, however, require a stable engine that survives the event. Recent 2026 observations from the FAST telescope captured rotation measure flares and repeating bursts. This twisting of the magnetic signal strongly implies the magnetar is interacting with the plasma wind of a companion star. In these binary systems, the magnetar's radio beam is likely passing through the dense magnetic exhalations of its larger neighbor. The companion star acts like a plasma lens, magnifying the burst and causing the signal's polarization to swing wildly before it escapes the system. So we have two engines producing one type of flash.
We have catastrophic mergers erasing the evidence, and stable binaries firing periodically through a plasma screen. The math for both mechanisms works perfectly within the hard constraints of neutron degeneracy. Viewing these models as wild guesses is a mistake. They are strictly governed by high-energy physics. The real problem is that we have not yet observed a delayed magnetar formation event, like a white dwarf collapse, in real time to confirm the signature. The ultimate test will be matching signals across different spectrums. Detecting a repeating fast radio burst perfectly coincident with a catastrophic gravitational wave event would shatter current models, because a repeating engine cannot survive the collision that produces those gravity ripples. There is always the possibility that our standard models are missing an exotic piece of physics. Some researchers argue that interacting cosmic strings or dark matter annihilation could generate these energies, though those theories lack the observational grounding that magnetar models currently enjoy. Regardless of which theory wins, one absolute truth remains. The universe requires multiple, distinct formation channels to explain the diverse environments where we find these bursts. A single unified blueprint for the engine room simply does not exist. We may not know exactly how every cosmic flash is forged, but even while theorists argue over the source, the flashes themselves are traversing intergalactic space. And right now, astronomers are using that exact journey to solve a completely different mystery, weighing the invisible matter of the entire universe. To weigh the entire universe, observational astronomers realized something profoundly practical. They didn't actually need to know what causes the millisecond flash to start using the light. They just needed to measure what the radio waves hit on their long journey to Earth. Regardless of whether a radio burst comes from a collapsing star or a merging binary system, the waves must still travel across billions of light years to reach us. And that journey is a brutal physical gauntlet. As the millisecond pulse crosses the dark void, it violently collides with free electrons scattered across intergalactic space. These collisions slow down the lower frequencies of the burst, arriving at our telescopes a fraction of a second later than the high frequencies. Astronomers call this measurable delay the dispersion measure. In recent years, scientists proved a direct mathematical link between how stretched out a signal becomes and exactly how far it traveled, a strict rule now known as the McCourt relation. The McCourt relation effectively turned these mysterious flashes into the most precise cosmic way stations ever discovered.
By reading the exact smear of the incoming radio wave, we can count the total number of electrons it passed through. This completely revolutionized modern cosmology, because for decades, astrophysics was haunted by the missing baryon problem. When scientists tallied up all the normal matter in the universe, every star, planet, and glowing cloud, half of it was just unaccounted for. The foundational math of the Big Bang insisted this matter had to exist, but no telescope could actually see it. It was too cold to emit X-rays and too impossibly thin to block incoming starlight. It remained entirely invisible. But it is absolutely not invisible to fast radio bursts. As these intense pulses sweep through the universe, they act like a deep space sonar, physically illuminating the hidden gaseous material that connects the threads of the cosmic web. By late 2025 and into 2026, dedicated observatories like the Deep Synoptic Array in California used thousands of hours of burst data to finally close the ledger on the universe's missing mass, pinpointing exactly where the matter was hiding. The incoming FRB data proved that over 70% of the universe's ordinary matter is suspended as diffuse, ionized gas drifting in the vast, empty voids between galaxies, exactly where the standard theoretical models predicted it should be. This represents the ultimate paradox of fast radio bursts right now. We have successfully taken a completely unsolved astrophysical anomaly and weaponized it into a highly functional, highly reliable instrument for measuring the deepest invisible structures of the universe. We might not know exactly what is pulling the cosmic trigger in those ancient stellar graveyards, but the radio light itself is already mapping the darkest, emptiest spaces of the cosmos with a level of precision we have never had before. But of course, the scientists hunting the original source are not simply giving up.
To finally end the fierce debate between dead magnetars and catastrophic mergers, we need to catch the flash the exact second it violently erupts. And doing that requires a completely new kind of real-time telescope network. What unprecedented hardware is coming online right now to permanently link the cosmic flash to the fire and finally tell us the true story? To finally sort these competing blueprints, the era of guessing based on delayed archival data has officially ended. The next phase of the hunt relies on real-time, precision targeting, and it requires wiring an entire continent into a single radio eye. The original CHIME telescope in Canada was historically brilliant at catching thousands of fast radio bursts as they washed over Earth, but it had a severe limitation in resolution. It could tell us roughly which galaxy a burst came from, but not the exact neighborhood. It was the astronomical equivalent of hearing a massive explosion and only being able to narrow it down to a specific city. To figure out if a burst was caused by a young magnetar or a stellar merger, astronomers needed the exact street address before the smoke cleared. That is exactly what the newly completed CHIME outrigger network was built to do. By synchronizing the main Canadian telescope with newly constructed radio dishes thousands of miles away in California and West Virginia, researchers created a massive continental interferometer. This technique, known as very long baseline interferometry, drastically sharpens the focus. It takes the positional uncertainty of a radio flash, previously the size of the full moon in the night sky, and shrinks it down to the equivalent of a coin held 40 kilometers away. In early 2026, this continental net proved its devastating precision. The network detected FRB 2025-0316A, an incredibly luminous one-off radio flash. But this time, the system didn't just flag the host galaxy and log the data. Within moments, the outriggers localized the burst with milli-arcsecond precision. They pinned the explosion to a microscopic 13-parsec radius inside a spiral arm of the galaxy NGC 4141, located 130 million light-years away from Earth. Because this sub-arcsecond coordinate was generated almost instantly, there was no delay. Astronomers immediately handed the exact cosmic address over to the James Webb Space Telescope for a rapid response infrared sweep before the environment could fade. When JWST pointed its mirrors at that exact 13-parsec radius, it achieved a historic first. It didn't just see a generic glowing gas cloud. Its high-resolution infrared sensors resolved the specific local stellar population right at the burst site. Webb identified a faint infrared source, designated NIR1, sitting dead center in a cluster of massive young stars. For the first time, we weren't just guessing the host environment. We were directly imaging the stellar nursery where the flash originated. Finding this burst locked inside a dense region of young stars strongly supports the idea that this specific flash was powered by a newly formed magnetar. But more importantly, this pipeline proves that we can now systematically autopsy these cosmic events. There is still a strict physical boundary to this method. Even with perfect, rapid localization, some flashes might leave absolutely no optical trace, meaning the progenitor object destroyed itself completely in the burst, leaving JWST staring into an empty void. Yet the fundamental shift in the science remains true. We are no longer waiting years to analyze a millisecond anomaly. By catching hundreds of bursts with sub-arcsecond precision, this real-time network will eventually force the universe to sort its flashes into clear, undeniable categories. The simple story of the fast radio burst is dead, replaced by a tangled web of extreme stellar physics. As these outrigger networks come fully online, the true story is finally coming into focus. Drop your theory on what causes these flashes in the comments. and subscribe to keep exploring the deep universe with us.